Hey folks, right? This is some old school Daft Punk. This is like from the year 2000. That's when I graduated high school, by the way. I was rocking out to Daft Punk 20 years ago, and I'm still rocking out to Daft Punk. Okay, let's get this thing going. Man, that song's 20 years old, and I still love it. Okay, awesome. Here we go. So we're getting into chapter 8. This is exciting stuff. So we're getting into Lewis structure. So that's going to be the main topic of this section. Okay. So, but before we get into Lewis structure, so in other words, Lewis structure is actually putting the shape of molecules together, right? Making molecules out of atoms. We got a few things to discuss related to chemical bonds, as you can see right here. So some of this is a review and some of this is new. Okay, so we've already talked about ionic bonds and covalent bonds this semester. And just a reminder, an ionic bond is a bond that is formed through mutual attraction between oppositely charged ions, right? So in an ionic bond, positive and negative ions get close to each other, but they don't necessarily make a formal bond like we view with a covalent bond. So a covalent bond is a bond formed when electrons are shared equally by nuclei. So we literally have like one atom and its electrons are being shared with another atom. So we draw like a line between those two atoms to represent that they are bound to each other, okay? So a polar covalent bond is a bond formed from unequal sharing, okay? So covalent bonds and polar covalent bonds are similar in that it is, two atoms bound to each other. However, there is that difference between sharing and unequal sharing. And we'll see on the periodic table, right? So you can tell I got a periodic table here, no calculations today. We'll talk about how we can tell when something is covalent or when something is polar covalent. All right. Okay, so metallic bonds. So that is a bond formed from nuclei of atoms surrounded by a sea of electrons. Okay. So what that means is in a metallic bond, we have these metals, right? Metal atoms, and they're just one right after the other, after the other, after the other. Okay. And we don't really view this as like a covalent bond, okay? It's more similar to this ionic bond in that you have attracted atoms to each other. But even so, it's still not even really so much like an ionic bond in that there's a positive and negative. And, metals, they're all neutral. They're not charged, okay? So you have this sea of electrons. So these metals that are all crammed, the atoms are crammed very close together, and you have these electrons that are kind of free to move throughout this extended network of atoms. Okay. So a delocalized electron are electrons that are shared among more than two atoms, right? So we talked about this covalent bond where there's electrons that make up this bond that are being shared by these two atoms. But now when electrons can be spread out through more than just two atoms, we say that they are delocalized. So localized means it's very specific, right, to a certain point. Delocalized means it's spread out. And of course, the bond length, we've already kind of seen that a little bit in chapter 7, the distance between nuclear centers of two atoms joined by a bond, right? So if we've got two atoms like this, technically it goes from the center of this atom to the center of this atom. So that would give us our bond length, okay? So let's move forward. So understand these definitions here. So I've got, right here's our learning goals. Understand all the different types of chemical bonds that we just discussed, okay? So there we go. Okay, so let's move on to this learning goal number 2. Okay, so Lewis structure. So I'm going to first introduce this concept of Lewis dot structure, and then we're going to get more into to these learning goals. I think maybe my learning goals are just a little bit out of order. Yep, number 3, know how to come up with Lewis dot structure. So a little out of order, but that's okay. So the Lewis dot structure is a chemical symbol for an atom surrounded by one or more dots representing the valence electrons. Okay? And so I introduced this concept of valence electrons in chapter 7. And we recognize the valence electrons makes up whatever row that atom is in. Okay? And so you notice here on this periodic table, what's missing is the D block, the transition metals. Okay? And that's because those transition metals, right, they make up mostly metallic bonding. In fact, they make up entirely, are made up of metallic bonding. So because they have that like sea of electrons that I described, we don't really draw Lewis structures for pure transition metals, okay? So we mostly just draw Lewis structures for ionic compounds or covalent compounds. So that's why you can see that this list is really just giving us the group 1 and group 2 metals, and then predominantly the nonmetals. So let's pick on carbon, for example. Okay, so there's carbon. And if I look at how many valence electrons it should have, if I start at this row, if I start at lithium, right, the 2s row, there's 1, 2, 3, 4 valence electrons for carbon, and here they are. Okay, 1, 2, 3, 4. They're kind of drawn, spread around the atom because they don't want to get next to each other if they don't have to. And so if we look at nitrogen, now nitrogen will have 5. And so now, of course, one of them is forced to be paired up. Oxygen will have 6. Fluorine will have 7. And of course, all of our noble gases, right, if we count, 1, 2, let me do this, 1, 2, 3, 4, 5, 6, 7, 8, right? And all of the noble gases will have 8 valence electrons, okay? And that's what we call a full shell, the octet rule. The tendency to gain or lose electrons to have a full shell. So that's 8 electrons, okay? And so we notice here oxygen, there's a reason why we always say oxygen is always 2 minus when it makes a compound, because if we notice here this oxygen atom, right, oxygen atom has 6 valence electrons, okay? When you give oxygen 2 extra electrons, so in other words, when you reduce oxygen, reduction is gain, right? And we make O2 minus, okay, that looks like the following. So it has the 8, okay? But now, when we draw Lewis structure of ions, okay, so this would be the Lewis structure for the oxygen atom. 6 electrons, we go 1, 2, 3, 4, 5, 6. Only pair them up if you have to, okay? But now when I make the oxide ion, right, I draw brackets around this thing and say 2 minus. And I also have to include those 2 extra electrons. Those 2 extra electrons give it the octet rule, okay? So what about something like, let's pick on magnesium. Okay, so magnesium, we can see is 1, 2 valence electrons, okay? Oops, I need to pause my, I need to mute my stereo because I hit a button by accident, and I don't want to do that again. Okay, so now this has, let's see here, 1, 2 electrons, okay? But now what happens is magnesium is not reduced, rather it is often oxidized, okay? Because if we wanted to reduce magnesium to give it the octet rule, I'd have to force 6 electrons onto magnesium to give it that octet rule. It doesn't want to do that, all right? Instead, it can lose 2 electrons, magnesium plus 2 electrons, and this would actually be the correct Lewis dot structure for magnesium. Just a magnesium with no dots and a 2 plus, okay? So we don't use that like noble gas convention like we did for electron configuration, because we want to represent that this is a magnesium ion we're talking about, okay?